advanced semiconductor manufacturing is hitting a critical chemical purification bottleneck. Propylene glycol methyl ether acetate, or PGMEA, is the primary solvent vehicle for advanced lithography. The transition to sub-7 nanometer nodes requires ultra-high purity solvent with metal impurities below 10 parts per trillion. Global demand for this 10 parts per trillion grade is expanding at an 8.2% compound annual growth rate. Effective purification capacity entered a structural deficit of 2.3 kilotons in 2022. This supply gap is projected to widen to 19.7 kilotons by 2026. The deficit is driven by lagging capital expenditure in high-purity fractional distillation columns. Furthermore, upgrading purification from 100 parts per trillion to sub-10 parts per trillion reduces effective distillation yields by 25 to 30%. This yield penalty compounds the capacity shortfall. The supply chain for ultra-high purity PGME is highly consolidated. Taiwan and Japan collectively control 73% of global purification capacity. This extreme concentration exposes advanced chip fabrication to severe single point of failure risks. Mainland China produces large volumes of industrial-grade solvent. However, its domestic purification is limited to 50 parts per trillion or worse. This makes Chinese domestic supply unusable for advanced extreme ultraviolet lithography. The United States and Europe combined hold only 12% of global purification capacity. This geographic imbalance is a critical bottleneck for Western semiconductor onshoring initiatives. Fabs built in Arizona or Ohio remain entirely dependent on chemical imports from East Asia. Advanced lithography architectures are fundamentally more chemical-intensive. High numerical aperture extreme ultraviolet lithography requires thicker spin-on carbon layers and underlayers. This increases solvent consumption per wafer pass to 115 milliliters. Total solvent volume per 100 wafers scales from 3.1 liters in legacy dry nodes to 40.3 liters in high numerical aperture systems. This represents a 1,200% increase in chemical intensity. Continuous track cleaning and extreme ultraviolet pellicle requirements further escalate auxiliary solvent use. The physical reality of chemical transport and storage is now a primary constraint on fab throughput. Software optimization cannot bypass this material bottleneck. Brazil's agricultural expansion is structurally limited by inland transportation friction. Historically, the agricultural heartland of Mato Grosso relied entirely on southern ports located over 2,000 kilometers away. The paving of the final unpaved segment of the BR-163 highway in late 2019 fundamentally altered this trade dynamic. This single infrastructure corridor unlocked the Northern Arc logistics network. Northern Arc ports increased their share of national grain exports from 15.8% in 2013 to 34.2% by 2023. This represents a structural reallocation of over 30 million metric tons of grain annually. The shift has directly relieved chronic congestion at the southern ports of Santos and Paranaguá. Post-2019, the Northern Arc market share expanded at a compound annual growth rate of 6.1%. Physical infrastructure investment has successfully bypassed legacy rail and road bottlenecks in the south. The efficiency gains of the Northern Arc route are driven by geography. Trucking distance from northern Mato Grosso to the Miritituba barge terminal is 1,050 kilometers. This is exactly half the 2,100-kilometer overland haul required to reach Santos. From Miritituba, high-capacity barge convoys transport grain down the Tapajos and Amazon rivers to deepwater terminals. This fluvial connection reduces maritime transit times to both Europe and Asia by an average of 5 days. It bypasses the congested shipping lanes of the South Atlantic entirely. These physical shortcuts yield substantial microeconomic advantages. Total logistics cost savings average $22 per metric ton. This translates to approximately $700 million in annual systemic savings for agricultural producers. Despite these structural gains, the Northern Arc remains highly vulnerable to seasonal hydrology. The Tapajos and Amazon river systems experience severe draft limitations during the equatorial dry season. From September to November, water levels drop rapidly. During the peak dry season in October and November, river depths fall below 2.0 meters. This forces operators to reduce barge drafts, cutting convoy capacity to as low as 30% of nominal limits. Maximum convoy capacity drops from 40,000 metric tons to just 12,000 metric tons. This seasonal bottleneck exposes the limits of relying on natural waterways without continuous capital-intensive dredging. When river levels drop, grain must either be stockpiled at high cost or rerouted back to southern ports. Physical geography and climate continue to impose hard limits on logistical optimization. Compound semiconductors like gallium arsenide and indium phosphide are replacing silicon in high-frequency and optoelectronic applications. These technologies depend entirely on ultra-high-purity metallic arsenic refined to 7N and 8N grades. The upstream supply chain for this material is highly consolidated. China controls 120.0 metric tons per annum of refining capacity. This represents 92.3% of the global total. Alternative capacity is fragmented across Japan and Germany. The United States possesses zero domestic primary refining capacity for 8N arsenic. This creates a single point of failure vulnerability for Western defense systems and telecommunications infrastructure. Global demand for high-purity arsenic is accelerating. Total consumption expanded from 71.8 metric tons in 2019 to an estimated 118.7 metric tons in 2024. This represents a compound annual growth rate of 10.6%. Radio frequency microelectronics remain the primary volume driver. Gallium arsenide power amplifiers for 5G and 6G infrastructure consumed over 57% of total supply in 2024. Simultaneously, high-growth optoelectronic applications are expanding at 12.6% annually. These include indium phosphide laser diodes for fiber optic networks and vertical cavity surface-emitting lasers for automotive LiDAR. This demand surge intensifies the geopolitical risk of the refined material bottleneck. High concentration of refining capacity is sustained by severe technical barriers. Transitioning from crude smelter byproducts to semiconductor-grade metal requires a complex four-stage thermal and chemical process. The cumulative material yield of this process is only 9.6%. Purification must reduce critical impurities like sulfur and silicon to subparts per billion levels. The highest 8N grade requires transition metal concentrations below 10 parts per trillion. The highly toxic nature of arsenic vapor processing imposes strict environmental and regulatory constraints. These physical and chemical realities prevent rapid capital deployment from establishing alternative refining capacity. The bottleneck is structural and cannot be bypassed quickly. The Baku-Tbilisi-Kars railway is designed to bypass Russian territory by connecting Central Asia to Europe. However, a stark divergence exists between nominal capacity and actual operational throughput. In mid-2024, a $120 million modernization expanded nominal capacity from 1 million to 5 million metric tons per annum. Yet, actual throughput for 2024 reached only 1.2 million metric tons. This represents a low capacity utilization rate of 24%. The bottleneck is not the rail line itself, but the physical transition point at the border. While historical demand grew at a 25.9% compound annual rate, physical constraints limit real-world volumes. The system cannot scale without resolving the mechanical friction of the border crossing. The primary friction point is the gauge break at the Akalkalaki terminal in Georgia. Here, trains must transition from the Russian 1520 mm broad gauge to the standard 1435 mm European gauge. This mechanical transition requires either physical container transshipment or bogie wheel assembly exchange. In 2023, total processing delays peaked at 60 hours per block train. This was driven by cargo diverting from the northern Russian route. Even after recent upgrades, mechanical operations alone consume 15 hours per train. This single terminal transition accounts for over 15% of the total transit time between Baku and Kars. Physical infrastructure limitations dictate these delays. Software optimization cannot bypass the mechanical reality of changing wheel sets. These physical delays directly undermine the economic competitiveness of the middle corridor. At 18 days, transit via the Baku-Tbilisi-Kars route is 4 days slower than the northern route through Russia. It also carries a 50% cost premium, reaching $4,200 per 40-foot equivalent unit. This premium is driven by the labor and equipment costs of repeated cargo handling across 3 transshipment points. Furthermore, mechanical bottlenecks in Caspian Sea weather limit the route's reliability index to 65%. Until these physical constraints are resolved, the corridor cannot fully compete with Northern Rail or standard maritime routes. Geopolitical desire to bypass Russia remains constrained by the hard realities of steel and track gauge. Advanced memory manufacturing is constrained by a critical chemical precursor bottleneck. As 3D NAND flash architectures scale vertically, traditional silicon precursors fail to meet strict thermal budgets. Hexachlorodisilane, or HCDS, enables low-temperature atomic layer deposition of silicon nitride films below 550 degrees Celsius. This thermal window is mandatory to prevent degradation of underlying tungsten word lines. Global HCDS demand is scaling from 180 metric tons in 2018 to an estimated 790 metric tons by 2026. This represents a compound annual growth rate of 20.3%. The transition from legacy 96-layer architectures to advanced 280-plus layer designs drives a 290% increase in the per-wafer consumption index. The vertical scaling of memory channels requires an exponential multiplication of alternating oxide nitride deposition steps. Alternative precursors cannot match the deposition rate of HCDS at low temperatures. Consequently, physical memory density is now directly bound to the volume and purity of this single chemical precursor. The supply chain for high-purity HCDS is highly consolidated and geographically vulnerable. East Asian chemical manufacturers control 73% of global 6N to 7N purification capacity. Japan and South Korea combined command over 70% of this market. South Korea has expanded its share to 35% to support domestic memory fabrication. Achieving 6N purity requires continuous multi-stage fractional distillation. A single thermal fluctuation in these columns can contaminate an entire production batch, causing weeks of downstream fabrication delays. The manufacturing process is highly sensitive to power grid instability and raw material input variations. Logistical friction further compounds this supply chain vulnerability. HCDS is highly pyrophoric and corrosive, requiring Class 8 and Class 4.3 hazardous material packaging. This physical hazard restricts transoceanic transport to specialized temperature-controlled ISO tank containers. Air freight is legally prohibited as an emergency backup, making the global memory supply chain highly sensitive to localized maritime disruptions. The industrial circulatory system of North America relies on a severely degraded maritime defense against winter ice. The United States Coast Guard's Great Lakes icebreaking fleet is anchored by a single heavy vessel and 8 aging tactical tugs. 6 of these 8 tactical tugs have already exceeded their 40-year engineered design life. This extreme asset age directly impairs operational readiness. The average winter availability of these overaged tugs has dropped to 63.5% due to compounding mechanical failures. This leaves the region highly vulnerable to sudden freeze events. The sole heavy icebreaker, the cutter Mackinac, maintains an 88.5% availability rate. However, this single vessel represents a critical single point of failure for the entire St. Mary's River Transit Corridor. A single unscheduled maintenance event on the Mackinac can halt the flow of essential raw materials. Physical ice formation directly dictates the volume of industrial manufacturing in the American Midwest. During the severe winter of 2013 to 2014, peak ice cover reached 92.5%. Consequently, bulk cargo throughput fell to just 6.2 million metric tons. This represents a 50.4% drop compared to the historically mild winter of 2023 to 2024. High ice seasons generate an average of $503.7 million in regional economic losses. These losses stem from vessel delays, hull damage, and forced production slowdowns at integrated steel mills. Furthermore, the official closure of the Soo locks does not define the real limits of the shipping season. Inadequate icebreaking capacity regularly extends the transit shutdown by 14 to 21 days on either side of the official window. Software and logistics algorithms cannot bypass this physical barrier. Only steel hulls and horsepower can clear the path. Advanced industrial systems are hitting a metallurgical wall. The production of corrosion-resistant Nickel-Chromium-Molybdenum superalloys requires highly specialized thermal processing. Vacuum induction melting, or VIM, is the primary bottleneck. Global VIM capacity utilization reached 96.2% in 2024. This leaves virtually zero operational buffer for scheduled furnace maintenance or refractory relining. Consequently, Average lead times for specialized alloy forgings escalated from 18.0 weeks in 2018 to 52.5 weeks in 2024. This represents a 191.6% increase in procurement latency. Global demand for these superalloys expanded at a 6.1% compound annual growth rate post-2020. The surge is driven by deep geothermal drilling initiatives and advanced chemical reactor construction. The geographic distribution of VIM infrastructure exacerbates Western supply chain vulnerabilities. The United States and Europe control 53.5% of global operational capacity, representing 113,000 metric tons. However, they carry 63.0% of the global order backlog. This mismatch creates severe project delays for domestic energy and chemical infrastructure. China operates 55,000 metric tons of capacity, but its output is heavily prioritized for domestic aerospace and military programs. This domestic focus limits export relief for Western industrial buyers. The global backlog-to-capacity ratio now stands at 75.0%. Existing orders represent 9 months of continuous, uninterrupted global VIM furnace output. Physical capacity constraints cannot be bypassed by software optimization. They require capital-intensive, multi-year metallurgical expansions. Lutetium is the heaviest and rarest stable lanthanide. It represents only 0.4% of the rare earth oxide content in southern Chinese ion adsorption clays. Securing 1 metric ton of lutetium oxide requires processing 250 metric tons of raw rare earth oxides. This extreme physical scarcity is compounded by geopolitical concentration. China controls 93% of global refining capacity for 5N-grade lutetium oxide. The purification process requires up to 1,000 stages of continuous countercurrent solvent extraction. This hydrometallurgical separation relies on hazardous organophosphorus solvents to isolate lutetium from adjacent ytterbium and thulium. The high chemical complexity and environmental footprint prevent rapid capacity duplication outside of China. The upstream supply chain is a near monopoly. Global demand for 5N lutetium oxide is expanding rapidly. Consumption grew from 12.5 metric tons in 2018 to an estimated 25.5 metric tons in 2024. This represents a 12.6% compound annual growth rate. This demand is directly coupled to the medical imaging market. A single positron emission tomography scanner requires up to 150 kilograms of scintillation crystal. Global scanner shipments reached 2,650 units in 2024. Inelastic supply has triggered an extreme price response. The market price for 5N lutetium oxide surged 190% between 2020 and 2024. Prices peaked at $1,600 per kilogram due to structural deficits and export anxieties. Securing raw lutetium does not resolve the downstream manufacturing bottleneck. Growing scintillation crystals via the Czochralski method requires temperatures of approximately 2,050 degrees Celsius. This extreme thermal environment limits crystal boule yields to between 38 and 45%. Thermal stress cracking and stoichiometry drift cause high scrap rates. Furthermore, the process requires iridium crucibles, which are the only vessels capable of withstanding these temperatures. These crucibles experience up to 1.8% material loss per run, escalating capital costs. These physical constraints have severely delayed medical hardware production. Average lead times for detector modules tripled from 16 weeks in 2020 to 48 weeks in 2024. The bottleneck is fundamentally metallurgical and thermal, resisting simple software or logistical workarounds.